There's a number so large that it breaks your brain just trying to hold it there. 93 billion light years. That is how wide the observable universe is, the distance from one edge of everything we can possibly see to the other edge. 93 billion light years of space, filled with hundreds of billions of galaxies, each containing hundreds of billions of stars, and we measured it. Humanity, with our brief lives and our tiny planet, figured out how to measure the immeasurable. But here is the beautiful, unsettling twist. That is just what we can see. The actual universe, the whole thing beyond our cosmic horizon, might be infinite. We live in a bubble, 93 billion light years across, floating in something that might go on forever. And tonight, we're going to explore how we discovered this, how we went from thinking the universe was small enough to wrap our minds around, to realizing it is so vast that even our most sophisticated mathematics struggles to contain it. Hello, and welcome to the Sleepy Astronomer. If you are joining me for the first time, welcome to this gentle journey to the edge of everything. And if you have travelled with me before through cosmic mysteries and impossible distances, it's wonderful to have you back for another exploration. Whether you're settling into bed, finding a quiet moment after a long day, or perhaps lying somewhere under a sky full of stars that are closer than you think, I am so glad you're here to explore this question with me. If you enjoy these peaceful drifts through the cosmos, I would be ever so grateful if you would subscribe to the Sleepy Astronomer for more journeys like this one. And if this question intrigues you, how big is the universe really? A gentle light helps others find their way to these nocturnal wonderings about space and scale. Here is something that might surprise you. For most of human history, we thought the universe was tiny. Not metaphorically tiny, actually small. The ancient Greeks calculated the cosmos to be perhaps a few million miles across. Medieval scholars imagined crystalline spheres just beyond the planets, with heaven sitting comfortably outside. Even into the early 20th century, we thought our galaxy was the entire universe, and that galaxy was only a few thousand light years wide. We were so beautifully, confidently wrong. Every time we built a better telescope, invented a more clever way to measure distance, or pieced together a new insight about how light and space and time actually work, the universe got bigger, and then bigger still. The edge kept moving. Not because the universe was growing, well, it is growing, but that is another matter, but because we kept discovering how much more of it there was to see. So this is not just a story about a number. It is a story about human persistence in the face of the incomprehensible, about building cosmic distance ladders rung by careful rung, about making mistakes and correcting them, and slowly, patiently, measuring our way to the edge of observable reality. Tonight, we will follow that journey, from the first astronomers who dared to measure beyond Earth, to the cosmic microwave background that gave us the universe's baby picture, to the James Webb Space Telescope showing us galaxies forming just after the Big Bang. We will learn why the universe is 93 billion light years wide, even though it is only 13.8 billion years old. That bit of math is wonderfully strange. We will discover what it means to live inside an observable bubble with an edge we can never cross. And we will sit with the humbling, beautiful realization that we are small beyond imagining. Yet we somehow figured out how big the stage is on which we stand. So take a deep breath. Let your shoulders drop. Get comfortable. The question is simple. How big is the universe? The answer is, well, it depends on what you mean by universe. Picture a man standing next to a well in ancient Egypt. watching the summer sun climb to its highest point in the sky. The sun shines straight down into the well, illuminating the water at the bottom with no shadow at all. It is noon on the summer solstice in the city of Siena, and this particular well is rather famous for this very phenomenon. Once a year, the sun looks directly down its shaft. Now picture another man, 250 miles north in the city of Alexandria, watching a tall tower cast a shadow at that exact same moment. Same sun, same time, different shadow. And from this simple observation, one well with no shadow, one tower with a shadow, a librarian named Eratosthenes was about to measure the entire Earth. It is around 240 BCE. Eratosthenes has heard about the shadowless well in Siena. He knows that at the exact same moment in Alexandria, vertical objects cast shadows. This should not be possible if the Earth is flat. But if the Earth is curved, if it is a sphere, then the sun's rays would hit different parts of that sphere at slightly different angles. The geometry writes itself. Eratosthenes measures the angle of the shadow in Alexandria. 7 degrees. He knows the distance between Alexandria and Siena, about 5,000 stadia, a stadium being a unit of measurement that, let us be honest, historians still argue about. But the principle is flawless. 7 degrees is 1/50th of a circle's 360 degrees. So the full circumference of Earth must be 50 times the distance between the two cities. His answer: 250,000 stadia. Depending on which stadium length you use, this translates to somewhere between 24,000 and 29,000 miles around. The actual circumference of Earth is about 24,900 miles. He was astonishingly close, using shadows and geometry and the assumption that the sun is far enough away that its rays arrive essentially parallel. This ancient librarian measured the entire planet without ever leaving Egypt. Here is what makes this extraordinary. Eratosthenes proved something profound about the universe. You can measure what you cannot directly observe. You can figure out the size of something enormous by measuring something small. You need only understand the geometry, gather the right observations, and trust that the universe follows consistent rules. This principle, measuring the unmeasurable through clever indirect methods, becomes the foundation for everything that follows. Every cosmic measurement we have ever made traces back to this insight. We cannot stretch a tape measure to the moon or the sun or the nearest star, but we can observe, calculate, and deduce. We can build ladders of inference that reach across distances our bodies will never cross. The beautiful thing about Eratosthenes' method is how it turned a limitation into a tool. He could not travel around the world to confirm its roundness. He could not fly up into space to see Earth's curve. But he did not need to. The shadow did the work for him. The sun unwittingly became his measuring instrument, and the Earth itself, simply by being curved, revealed its own dimensions. This is the first lesson in measuring the unmeasurable. Let the universe do the measuring for you. Find the phenomenon that encodes the information you seek and learn to read it. After Eratosthenes came other bold calculators. Aristarchus of Samos, working around the same time, attempted to measure the distances to the moon and the sun. His method was elegant. During a half moon, the Earth, moon, and sun form a right triangle. If you measure the angle between the moon and sun from Earth perspective, you can use trigonometry to figure out the ratio of their distances. Aristarchus's execution was less elegant than his idea. His instruments were not precise enough to measure the tiny angle accurately. He concluded the sun was about 20 times farther away than the moon. The actual number is closer to 400 times. But again, the principle was sound. The cosmos could be measured. It was just a matter of better tools and more careful observations. What is remarkable about these ancient attempts is not their accuracy, though Eratosthenes came impressively close, but their audacity. These were people living in a world without telescopes, without calculus, without even accurate clocks. They had geometry and shadows and an insatiable curiosity about the structure of the cosmos. And they looked at wells and towers and the phases of the moon and thought, "We can figure this out." For nearly 2,000 years after these Greek geometers, humanity's picture of the cosmos remained comfortably small. Earth at the centre, sun and moon and planets circling nearby, stars embedded in a distant but reachable sphere. It was a cosy universe, human-scaled, comprehensible. The dome of stars might be far away, but it was still a dome, a boundary, an edge, something that enclosed and defined the extent of creation. Then came the telescope. Galileo pointing his improved spyglass at the heavens in 1609, seeing mountains on the moon, moons orbiting Jupiter, phases of Venus, countless stars invisible to the naked eye. Each observation pushed the boundaries outward. If Jupiter has moons, then Earth is not the centre of all motion. If Venus shows phases like our moon, it must orbit the sun. If there are vastly more stars than we can see unaided, how far away might they be? But seeing farther is not the same as measuring distance. The stars remained infinitely far away in practical terms, tiny points of light with no discernible size, no measurable parallax, no way to gauge their distance. You could see more of them through a telescope, but you could not tell if they were small and nearby or enormous and distant. The universe suddenly contained multitudes, but those multitudes remained frustratingly unmeasured. Parallax. Let us pause here, because this becomes crucial. Hold your thumb up at arm's length. Close your left eye and note where your thumb appears against the distant background. Now close your right eye and open your left. Your thumb appears to shift position against the background. This apparent shift is parallax, and it happens because your two eyes view your thumb from slightly different positions. The same principle works for stars, in theory. As Earth orbits the Sun, we view nearby stars from different positions 6 months apart. That is a baseline of about 186 million miles, the diameter of Earth's orbit. Surely, with that much separation, nearby stars should appear to shift against the background of more distant stars. And yet, for centuries, no one could detect this shift. The problem was not the theory. The problem was that stars are so phenomenally far away that even with Earth's vast orbit as a baseline, the parallax angles are almost invisibly small. The nearest stars shift by less than 1 arc-second, 1/3600th of a degree. Try measuring that with a telescope that wobbles in the wind, mounted on a planet that is rotating and wobbling on its axis, while you yourself are standing on that planet trying to hold very, very still. For 200 years after the telescope was invented, astronomers tried and failed to measure stellar parallax. Some began to wonder if stars might be so distant that parallax was simply unmeasurable. Others suggested, correctly as it turned out, that we just needed better instruments and more patience. The failure to detect parallax actually strengthened the arguments of those who believed Earth was stationary at the centre of the universe. If Earth truly orbits the Sun, they reasoned, we should see stellar parallax. We do not see it. Therefore, Earth must not be moving. It was an understandable conclusion and completely wrong. The stars were simply much, much farther away than anyone had dared to imagine. In 1838, Friedrich Wilhelm Bessel finally succeeded. Bessel was a German astronomer and mathematician, the kind of person who calculates orbits for fun and develops new mathematical functions in his spare time. He chose a star called 61 Cygni in the constellation Cygnus the Swan. He chose it not because it was bright, it is rather dim actually, but because it moves quickly across the sky relative to background stars. This large proper motion suggested it might be relatively close. For over a year, Bessel made meticulous measurements using a heliometer, an instrument that could measure tiny angles with unprecedented precision. He watched 61 Cygni shift back and forth against distant background stars as Earth orbited the Sun. The shift was minuscule, about 1/3 of an arcsecond. Imagine trying to measure the width of a human hair from 60 feet away. That is the scale of precision required. From this tiny angle, Bessel calculated the distance, about 660,000 astronomical units, or roughly 10.4 light-years. Modern measurements put 61 Cygni at 11.4 light-years away, so Bessel was remarkably accurate. But the number itself is less important than what it represented. For the first time in human history, we had measured the distance to a star. We had extended our cosmic measuring tape beyond the solar system. The technique Aristarchus had theorized about, the parallax that Copernicus had predicted, was finally, definitively measured. And the distance was staggering. 10 light-years means the light we see from that star left its surface 10 years ago. It means that star is about 60 trillion miles away. It means the space between stars is vastly, almost incomprehensibly, empty. To put this in perspective, if the Sun were the size of a grapefruit sitting in the centre of a football field, Earth would be a grain of sand about 25 yards away, and the nearest star, using this same scale, would be another grapefruit sitting roughly 2,000 miles away. The distances between stars are so enormous that even our solar system, which feels vast when we consider the journey to Mars or Jupiter, is barely a dot in comparison. The same year, 1838, two other astronomers also succeeded in measuring stellar parallax. Thomas Henderson measured Alpha Centauri from the Cape of Good Hope. Friedrich von Struve measured Vega from Russia. After 2 centuries of failure, 3 astronomers independently achieved success within months of each other, a testament to how rapidly telescope and measurement technology was improving. There is something beautiful about that simultaneous success, as if the universe had been waiting for us to build sufficiently precise instruments before revealing this particular secret. These first stellar distance measurements confirmed something that Copernicus and Galileo had suggested, but could not prove. Earth truly does orbit the Sun. If Earth were stationary, there would be no parallax. The apparent shift of nearby stars was direct geometric proof of Earth's motion through space. It vindicated centuries of astronomical theory and silenced the last serious objections to the heliocentric model. But they also revealed something more unsettling. If the nearest stars are 10 or 11 light-years away, and there are countless thousands of stars visible in telescopes, and the Milky Way band stretching across the sky contains countless more, how large is the cosmos really? The answer, much larger than anyone had imagined, and we had only just begun to measure it. The parallax method works beautifully for nearby stars, but it has limits. Beyond a few hundred light-years, parallax angles become too small to measure accurately, even with modern instruments. For a long time, this seemed like an absolute barrier. If we cannot measure parallax, how can we know distance? The answer would come from watching stars that pulse, from measuring how bright things appear, from finding cosmic lighthouses whose rhythms could be read like clocks, revealing distances far beyond the reach of parallax. From Eratosthenes and his well to Bessel and his star, humanity learned to measure what seemed unmeasurable. We learned that the universe follows rules, that geometry and light and patient observation can reveal distances far beyond our physical reach. We learned that sometimes you must wait centuries for your instruments to catch up with your theories, and we learned that the moment you successfully measure one thing, you immediately discover how much farther everything else is. We learned that we live in a cosmos vastly larger than our ancestors imagined, and we learned that the edge, wherever it might be, keeps moving farther away the more carefully we look. The first measurers gave us the tools. Now we just needed to build the ladder tall enough to reach the edge of everything. Let that distance settle in your mind. 10 light years to the nearest stars, 60 trillion miles, and we have barely begun. Imagine trying to measure the distance to something impossibly far away. Say, a mountain on the horizon. You cannot walk to it. You cannot throw a measuring tape that far, but you can measure the distance to a nearby tree, and from that tree you can sight angles to a further landmark, and from that landmark you can triangulate to the mountain. Each measurement builds on the previous one, creating a chain of known distances that eventually reaches your target. This is how we measure the universe, not with a single method that works everywhere, but with a ladder of techniques, each one calibrated against the previous rung, each one reaching a bit farther into the cosmic distance. It is called, appropriately enough, the cosmic distance ladder. And like any ladder, if one of the lower rungs is wrong, everything above it becomes uncertain. We have already climbed the first rung, parallax. Bessel and his contemporaries measured nearby stars using Earth's orbit as a baseline, giving us solid distances out to a few hundred light years. This becomes our foundation, our known distances against which we can calibrate everything else. But the universe is vastly larger than a few hundred light years. The Milky Way galaxy alone is about 100,000 light years across, and there are billions of other galaxies beyond our own, some billions of light years away. Parallax cannot reach that far. We need a different method. We need standard candles. A standard candle is any astronomical object whose absolute brightness, its true luminosity, is known. If you know how bright something actually is, and you measure how bright it appears from Earth, you can calculate its distance. The math is straightforward. Apparent brightness decreases with the square of the distance. Double the distance and the object appears 1/4 as bright. Triple the distance, 1/9 as bright. It is the same reason a flashlight looks dimmer the farther away it moves. The light spreads out over a larger area. The trick, of course, is finding objects whose true brightness you can trust. And for that, we need stars that announce their luminosity through their behavior, stars that wear their brightness on their sleeves, so to speak. Enter the Cepheid variables. Cepheid variables are massive, pulsating stars that brighten and dim with remarkable regularity. Some pulse every few days, others pulse every few weeks or months. They are not exploding or dying. They are breathing, expanding and contracting in a steady rhythm driven by the physics of their outer layers. As the star expands, it cools and dims. As it contracts, it heats and brightens. The cycle repeats with metronomic precision. And here is the extraordinary thing, the period of pulsation, how long it takes to complete one cycle, is directly related to the star's true luminosity. A Cepheid that pulses slowly is intrinsically brighter than one that pulses quickly. The relationship is precise and predictable. If you measure the period, you know the luminosity. And if you know the luminosity and measure the apparent brightness, you can calculate the distance. It is that simple and that powerful. This period luminosity relationship was discovered by a woman named Henrietta Swan Leavitt in 1912. Leavitt worked at the Harvard College Observatory as one of the computers, women hired to analyze photographic plates of the night sky, measuring and cataloguing stars while male astronomers got the credit for discoveries. It was tedious work, repetitive and undervalued, but Leavitt approached it with extraordinary care. She was studying stars in the Magellanic Clouds, two small galaxies visible from the southern hemisphere. She noticed that some stars varied in brightness over time, and she began measuring their periods and apparent brightness. She found a pattern. The brighter a Cepheid appeared, the longer its period. And because all these Cepheids were in the Magellanic Clouds, roughly the same distance from Earth, their apparent brightness differences reflected true luminosity differences. Leavitt published her findings in 1912. Her paper was short, understated, and revolutionary. She had discovered a cosmic yardstick, a way to measure distances far beyond the reach of parallax. Yet she received little recognition during her lifetime, and she died in 1921 at age 53, never knowing how profoundly her work would change astronomy. Her name deserves to be mentioned in the same breath as Galileo and Hubble, yet it remains far less known. Using Leavitt's period luminosity relationship, astronomers could now identify Cepheid variables in distant star clusters and galaxies, measure their pulsation periods, calculate their true luminosities, and determine their distances. It was the second rung of the ladder, and it reached thousands, then tens of thousands, then hundreds of thousands of light years into space. In the 1920s, an astronomer named Edwin Hubble, working at the Mount Wilson Observatory with what was then the world's largest telescope, turned his attention to fuzzy patches of light called nebulae. Many astronomers believed these nebulae were gas clouds within our own Milky Way galaxy, but Hubble found Cepheid variables within some of these nebulae, measured their distances using Leavitt's relationship, and discovered something extraordinary. These nebulae were not in our galaxy at all. They were other galaxies, separate islands of stars millions of light years away. The Andromeda Nebula was actually the Andromeda Galaxy, over 2 million light-years distant. The universe was suddenly dramatically larger than anyone had imagined. The Milky Way was not the universe. It was one galaxy among countless others. This was a discovery on par with Copernicus displacing Earth from the center of the solar system. We were not even at the center of the galaxy, let alone the universe. We were residents of one ordinary galaxy in an ocean of galaxies, drifting through space with billions of other island universes all around us. But Cepheid variables, as wonderful as they are, have their limits too. Beyond about 100 million light-years, even bright Cepheids become too faint to detect reliably with most telescopes. To reach farther, we need an even brighter standard candle. We need exploding stars. Specifically, we need Type Ia supernovae. A Type Ia supernova occurs when a white dwarf star, the dense remnant of a star like our Sun, accumulates matter from a companion star until it reaches a critical mass, at exactly 1.4 times the mass of the Sun, a limit called the Chandrasekhar limit, after the astrophysicist who calculated it. The white dwarf can no longer support itself against gravity. It collapses and then explodes in a thermonuclear detonation of staggering violence. Here is what makes Type Ia supernovae useful. Because they all explode at the same mass, they all release roughly the same amount of energy. They are not exactly identical. There are variations we have learned to account for, but they are consistent enough to serve as standard candles, and they are astonishingly bright. For a few weeks, a single Type Ia supernova can outshine an entire galaxy of hundreds of billions of stars. This means we can see them across billions of light-years of space. In the 1990s, two independent teams of astronomers used Type IR supernovae to measure distances to extremely remote galaxies. They were trying to determine how fast the universe's expansion is slowing down. Everyone expected expansion to be slowing. Gravity from all the matter in the universe should be pulling everything back together, gradually decelerating the expansion that began with a Big Bang. But the measurements showed something else entirely. The expansion was not slowing, it was accelerating. Distant supernovae were dimmer than they should be, meaning they were farther away than expected, meaning the universe had expanded more than predicted. Something was pushing space apart, causing galaxies to recede faster and faster. This discovery earned the Nobel Prize in Physics in 2011 and introduced us to one of the deepest mysteries in cosmology, dark energy. We will return to this strange force later, but for now, let us simply appreciate what Type Ia supernovae gave us. Distances measured across billions of light years, nearly to the edge of the observable universe. The cosmic distance ladder now has three major rungs. Parallax for nearby stars, up to a few thousand light years. Cepheid variables for nearby galaxies, up to about 100 million light years. Type Ia supernovae for distant galaxies, up to billions of light years. Each rung is calibrated against the one below it. We use parallax to measure distances to nearby Cepheids, which gives us the period-luminosity relationship. We use Cepheids to measure distances to galaxies where Type 1a supernovae occur, which calibrates the supernova brightness. And we use Type 1 supernovae to measure the most distant reaches of space. But here is the challenge. If any rung is wrong, everything above it is wrong too. If we miscalibrate the Cepheid relationship, our supernova distances will be off. If our parallax measurements have systematic errors, the entire ladder shifts. This is not a hypothetical problem. For decades, astronomers have argued about the exact value of the Hubble constant, the rate at which the universe is expanding. Different methods give slightly different answers, and that difference matters when you are trying to determine the size and age of the universe. Some measurements, using the cosmic distance ladder, suggest the universe is expanding at about 73 kilometers per second per megaparsec. Other measurements using the cosmic microwave background suggest about 67 kilometers per second per megaparsec. That might not sound like much of a difference, but it translates to billions of light years when you scale up to cosmic distances. It is a bit like building a skyscraper and discovering that your foundation is slightly tilted. Everything gets more and more misaligned the higher you go. Astronomers call this the Hubble tension, and it is one of the most important unsolved problems in cosmology today. Are our ladder rungs slightly miscalibrated? Is there new physics we do not understand? Or are both measurements correct and the universe is simply stranger than our current models allow? The answer is still unclear. Modern astronomy has deployed increasingly sophisticated tools to refine each rung. The Hipparcos satellite, launched in 1989, measured parallax for over 100,000 stars with unprecedented accuracy. Its successor, Gaia, launched in 2013, has measured parallax for nearly 2 billion stars, giving us a far more solid foundation for the ladder. The Hubble Space Telescope has observed Cepheid variables in dozens of galaxies, refining the period-luminosity relationship and pushing Cepheid measurements farther into space, and automated surveys scan the sky continuously, detecting supernovae within hours of their explosions, building databases of thousands of events that help us understand their variations and improve their use as standard candles. Each improvement tightens the measurements, reduces the uncertainties, and gives us more confidence in our cosmic distances. But the ladder remains exactly that, a series of steps, each dependent on the ones below it, each extending our reach a bit farther into the universe. And here is the beautiful thing. Despite the uncertainties, despite the debates about exact values, the ladder works. It is internally consistent. Distances measured by different methods agree with each other within reasonable margins. When we find a galaxy that contains both Cepheids and a Type Ia supernova, both methods give similar distances. The universe has not caught us in a fundamental mistake. What the cosmic distance ladder reveals is not just how far away things are, but how we can know anything about the universe at all. We are creatures bound to one small planet, observing distant lights in the sky. We cannot travel to other galaxies to measure them directly. We cannot place rulers across intergalactic space. But we can observe patterns. We can calibrate relationships. We can build chains of inference that reach across billions of light years. We can measure the immeasurable one careful step at a time. The ladder took us from our cosmic neighborhood to the edge of the observable universe. From stars we can almost touch, metaphorically speaking, to galaxies so far away that their light has been traveling toward us since before Earth existed. We built this ladder over more than a century, one rung at a time, each generation of astronomers adding their careful measurements to the structure. And the view from the top of that ladder, the distances we can now measure, the scale we can now comprehend, is staggering beyond words. Let yourself feel the height of that ladder, the distance it spans, the delicate chain of calibrations that makes it possible. We are still climbing. There is a moment in the history of science when everything changes. Not gradually, not through slow accumulation of evidence, but suddenly. A single observation that forces us to reimagine the entire cosmos, for our understanding of the universe's size. That moment came in 1929, when Edwin Hubble discovered something that should not have been possible if the universe was static and unchanging. Galaxies were running away from us, all of them, in every direction. The farther away they were, the faster they were receding. The universe, it turned out, was not sitting still. It was expanding. Let us back up slightly, because the story actually begins a bit earlier, with a man looking at galaxy spectra and noticing something peculiar. In the 1910s and 1920s, an astronomer named Vesto Slipher was working at Lowell Observatory in Arizona, photographing the spectra of spiral nebulae, those fuzzy patches that Hubble would later prove were galaxies. When you split light into its component colours, you see dark lines at specific wavelengths, where elements in the star's atmosphere absorb light. These spectral lines are like fingerprints, unique patterns that tell you what a star is made of. But Slipher noticed something odd. The spectral lines from most of these nebulae were shifted toward the red end of the spectrum, not by much, but consistently and measurably. A few nebulae showed blue shifts, but the vast majority were red shifted. This was the Doppler effect in action, the same phenomenon that makes an ambulance siren sound higher pitched as it approaches you and lower pitched as it moves away. Light from an object moving away from you gets stretched to longer, redder wavelengths. Light from an object moving toward you gets compressed to shorter, bluer wavelengths. Slipher's observations suggested that most of these spiral nebulae were moving away from Earth, but at the time no one understood why. Were they fleeing from us specifically? Were they all launched from some cosmic explosion? The implications were unclear. Enter Hubble in 1929. He combined Slipher's velocity measurements with his own distance measurements, using Cepheid variables to determine how far away these galaxies were, and plotted them on a graph. Distance on one axis, velocity on the other. The result was striking, a clear relationship. The farther away a galaxy was, the faster it was moving away from us. Twice as far, twice as fast. 3 times as far, 3 times as fast. The relationship was linear, direct, undeniable. This relationship became known as Hubble's law, and the rate of expansion became the Hubble constant. Measure a galaxy's distance, multiply by the Hubble constant, and you get its recession velocity. Simple, elegant, and revolutionary. But here is what makes this truly extraordinary. Galaxies are not actually moving through space. Space itself is expanding, carrying galaxies along with it. This is a difficult concept to grasp because we have no everyday experience with expanding space. We are used to objects moving through space, cars driving down roads, planets orbiting stars. But space itself growing, that requires a shift in thinking. Imagine a balloon with dots painted on its surface. As you inflate the balloon, the dots move apart from each other. But the dots are not moving across the balloon's surface. The surface itself is stretching, carrying the dots along. From the perspective of any dot, all the other dots appear to be moving away. And the farther away another dot is, the faster it seems to recede, simply because there is more stretching space between them. This is what is happening in the universe. Galaxies are like dots on the balloon's surface. Space itself is stretching, and as it stretches, galaxies move apart. The expansion does not have a center. Every point in space sees every other point moving away. We are not at the center of the expansion. Neither is any other galaxy. The expansion is happening everywhere, uniformly, all at once. This immediately explains several puzzling things. Why do distant galaxies appear to be fleeing from us? Not because we are special or because something is repelling them, but because space is growing. Why is the universe the same in every direction? Because expansion is uniform. There's no preferred direction or location. The expansion also means the universe had a beginning. If galaxies are moving apart now, they must have been closer together in the past. Run the clock backward and everything converges. Galaxies get closer and closer until eventually, about 13.8 billion years ago, everything we can see was compressed into an infinitesimally small point. The moment when expansion began is what we call the Big Bang. Hubble's discovery was the first observational evidence for the Big Bang theory. Before this, many scientists, including Einstein, believed the universe was eternal and static, unchanging across infinite time. Einstein had even added a term to his equations of general relativity, the cosmological constant, specifically to keep the universe from collapsing or expanding. When he learned about Hubble's observations, Einstein reportedly called this his biggest blunder. Ironically, the cosmological constant would return decades later to explain dark energy. But that is a story for later. For now, let us sit with the strangeness of expanding space. When we say a galaxy is 10 billion light-years away, what do we mean? The light we see from that galaxy left its surface 10 billion years ago. But in those 10 billion years, space has been expanding. The galaxy is not where it was when the light departed. It is much farther away now, perhaps 15 or 20 billion light-years distant, depending on the expansion rate. This introduces 2 different ways to measure distance in an expanding universe: light travel distance and co-moving distance. Light travel distance is how far the light has travelled to reach us, literally the time since the light was emitted, multiplied by the speed of light. If we see a galaxy whose light has been travelling for 10 billion years, the light travel distance is 10 billion light-years. Co-moving distance accounts for expansion. It is the distance to that galaxy right now, at this very moment, given how much space has stretched since the light was emitted. This distance is always larger than the light travel distance for distant objects. When we say the observable universe is 93 billion light-years across, we are talking about co-moving distance. The universe is only 13.8 billion years old, so the oldest light has only been travelling for 13.8 billion years. But the sources of that light have been carried away by expanding space, and they are now roughly 46.5 billion light-years away in every direction. Double that, and you get the 93 billion light-year diameter. It's a bit like watching someone walk away from you on a moving walkway. They are walking at a steady pace, but the walkway is also moving, so they end up much farther away than their walking speed alone would suggest. Now you might ask, if space is expanding, why are we not expanding? Why is Earth not getting bigger? Why is the Milky Way not stretching? The answer is that expansion only affects very large scales, distances between galaxy clusters. At smaller scales, other forces dominate. Gravity holds galaxies together. Electromagnetic forces hold atoms together. The expansion of space is real, but it is weak compared to these binding forces. It is only in the vast empty regions between galaxy clusters, where gravity is negligible, that expansion becomes noticeable. Think of it this way. Imagine you are on a raft in a river. The river is flowing. That is expansion. But you are tied to a dock. That is gravity. The flowing water does not carry you away because the rope holds you in place. Only things that are not tied down, distant gravitationally unbound objects, get carried by the current. The Milky Way and Andromeda galaxies are gravitationally bound to each other. They are in fact on a collision course, and will merge in about 4 billion years. Expansion is not strong enough to overcome their mutual gravity. But a galaxy cluster a billion light-years away, there is no significant gravitational connection, so it rides along with expanding space. This brings us to redshift, one of the most important concepts in cosmology. Remember how Slipher observed spectral lines shifted toward the red? That shift is caused by expansion. As light travels through expanding space, its wavelength gets stretched along with that space. The longer the light travels, the more space expands, the more the wavelength stretches, and the redder the light becomes. Cosmologists use redshift, denoted by the letter Z, to quantify how much the universe has expanded since the light was emitted. A redshift of Z equals 1 means the universe has doubled in size since that light began its journey. A redshift of Z equals 2 means the universe has tripled in size. The highest redshift galaxies we have detected, thanks to the James Webb Space Telescope, have redshifts around Z equals 13 or 14, meaning the universe has expanded by a factor of 14 or 15 since that light was emitted. Redshift gives us a direct measure of cosmic history. Every time we look at a distant galaxy, we are not just seeing far away, we are seeing far back in time, and the redshift tells us exactly how much the universe has changed since then. But here is a question that bothers many people. If the universe is expanding, what is it expanding into? The answer is nothing, or rather, the question assumes something that is not true, that the universe is an object sitting inside some larger space. But the universe is not expanding into anything. Space itself is all there is. When space expands, it is not claiming territory from some surrounding void. It is simply becoming more space. This is profoundly counterintuitive. We are used to things expanding into space. A balloon expands into the air around it. A city expands into the countryside. But the universe has no around it. There is no outside. The universe is everything, and everything is getting bigger. If the universe is infinite, which it might be, then it has always been infinite. An infinite universe expanding does not become more infinite. It simply means the distance between any 2 points grows over time. Every finite region of space stretches, but the whole remains infinite. If the universe is finite but unbounded, shaped perhaps like the surface of a 4-dimensional sphere, then it still does not expand into anything. The surface of a balloon is 2-dimensional and finite, yet it has no edge and no outside. It is complete in itself. The universe might be similarly self-contained, just with one more dimension. Either way, the expansion is not happening in space. The expansion is happening to space. Hubble's discovery in 1929 changed everything. It told us the universe has a history, a beginning, a direction. It told us that the edge of the observable universe is not a fixed boundary, but a receding horizon, always moving farther away as space continues to expand. It told us that measuring cosmic distances means grappling with the strange physics of dynamic space-time. And it raised a question that would haunt cosmology for decades. If the universe is expanding now, will it expand forever? Or will gravity eventually slow and reverse the expansion, causing everything to collapse back into a big crunch? The answer to that question would come much later, from observations of distant supernovae, and the answer would be far stranger than anyone expected. For now, let us simply appreciate the profound shift Hubble gave us. The universe is not static. Space itself is fluid, dynamic, growing. We live in a cosmos that is perpetually changing, where distances are not fixed but continuously increasing, where the very stage on which cosmic events unfold is itself in motion. Let that sink in. The ground beneath the stars, the fabric of space itself, is stretching, carrying everything apart, writing the story of cosmic expansion across billions of years. We are not just measuring distance, we are measuring history. Here is a strange truth. There are galaxies in the universe that we will never see, not because our telescopes are not powerful enough, not because they are hidden behind dust or obscured by other objects, but because the light from those galaxies will never, ever reach us. Not in 1 billion years, not in 1 trillion, not ever. We live inside a cosmic horizon, a boundary beyond which information simply cannot travel to us, and that boundary defines what we call the observable universe. The observable universe is not the whole universe. It is just the part we can see, the region of space from which light has had time to reach us since the Big Bang, and it turns out that region has very specific limits. Let us start with the number we mentioned at the beginning. 93 billion light-years. That is the diameter of the observable universe, the distance from one edge of everything we can possibly see to the other edge. But the universe is only 13.8 billion years old. How can we see something 93 billion light-years away if light has only been travelling for 13.8 billion years? The answer, as we touched on before, is expansion. Imagine light leaving a distant galaxy 13.8 billion years ago, just after the Big Bang. That light travels toward us at the speed of light, the fastest speed possible, covering about 6 trillion miles per year. But while that light is travelling, space itself is expanding. The galaxy the light came from is being carried away by that expansion, and so is the space the light is travelling through. By the time the light reaches us, 13.8 billion years later, the galaxy that emitted it is no longer 13.8 billion light-years away. It has been carried much farther by the expansion of space. In fact, it is now about 46.5 billion light-years away. And since we can see in all directions, the observable universe forms a sphere around us with a radius of 46.5 billion light-years, diameter 93 billion light-years. This boundary is called the particle horizon, or sometimes the cosmic light horizon. It represents the farthest distance from which light could have travelled to reach us, given the age of the universe and the expansion of space. But here is the unsettling part. This horizon is not just a current limitation, it is a permanent boundary. You might think, well, if we wait long enough, light from more distant galaxies will eventually reach us, expanding our observable universe. And in a static universe, you would be right. But our universe is not static. It is expanding, and not just expanding, but accelerating in its expansion. This acceleration, driven by dark energy, means that distant galaxies are receding from us faster and faster. For galaxies beyond a certain distance, beyond our cosmic horizon, they are receding so quickly that their light will never reach us. The space between us and them is growing faster than light can cross it. Imagine running on a treadmill that keeps speeding up. Even if you run as fast as you possibly can, if the treadmill accelerates beyond your maximum speed, you will never make progress forward. Light from distant galaxies faces the same problem. It travels toward us at light speed, but if space between us and them expands faster than light speed, the light makes no progress. It runs in place, never reaching us. This creates what cosmologists call the cosmological event horizon, the boundary beyond which events are forever hidden from us. Galaxies beyond this horizon exist. They are out there, filled with stars and planets and perhaps civilizations. But we will never see them. Their light will never reach us. For all practical purposes, they might as well be in a different universe. And here is the truly sobering realization. Because of accelerating expansion, our observable universe will actually shrink over time. Right now, we can see galaxies that are receding from us at speeds greater than light. They are already beyond the event horizon. But we see them because the light we are receiving left those galaxies billions of years ago, when they were closer and not yet beyond the horizon. We are seeing their past. In the future, as expansion continues to accelerate, fewer and fewer new galaxies will come into view. The most distant galaxies we can see now will fade from view as their light becomes too redshifted to detect. Eventually, trillions of years from now, observers in our galaxy will only be able to see the galaxies in our local gravitationally bound group. Everything else will have been carried beyond the horizon. Future astronomers, born in that distant era, will look out at the universe and see almost nothing. A few nearby galaxies and beyond them, darkness. They will have no way to know that billions of other galaxies once filled the observable universe. The evidence will have disappeared beyond the horizon. We are living in a cosmically privileged time. We can see the full history of the universe, the cosmic microwave background, from 380,000 years after the Big Bang, distant galaxies forming just a few 100 million years after the Big Bang, the full sweep of cosmic evolution. Future civilizations will not have that privilege. The universe will have pulled its curtains closed. Let us put this in perspective. Right now, the observable universe contains approximately 2 trillion galaxies, 2 trillion islands of stars, each with hundreds of billions of suns. But this is just what we can see. The actual universe, the whole thing beyond our horizon, is almost certainly much, much larger. How much larger? We do not know. Conservative estimates suggest the universe is at least 250 times larger than the observable universe. That would mean roughly 500 trillion galaxies exist in total. Others suggest the universe might be infinite, containing literally infinite galaxies. But we will never know for certain. We can only observe our bubble, our cosmic prison, the finite sphere of space from which light can reach us. Now you might wonder, if galaxies beyond the horizon are receding faster than light, does that violate Einstein's rule that nothing can travel faster than light? The answer is no, and here is why. Galaxies are not moving through space faster than light. Space itself is expanding, carrying galaxies along with it. The speed limit of light applies to motion through space, not to the expansion of space itself. There is no law that prevents space from expanding at any rate. Distant galaxies are not speeding away from us. They are being carried by the expanding fabric of space-time, and that expansion has no speed limit. Think of it like this. If you are on a moving walkway at an airport and you walk forward at 3 miles per hour, but the walkway is moving at 5 miles per hour, you are covering ground at 8 miles per hour relative to the stationary floor. You're not breaking any walking speed limit. You are simply benefiting from the motion of the surface beneath you. Galaxies benefit from the expansion of space beneath them, so to speak, allowing their recession speeds to exceed the speed of light without violating relativity. This also explains why we can see galaxies that are receding faster than light. The light from those galaxies is not travelling faster than light. It is travelling at exactly light speed, as it must. But when the light was emitted, those galaxies were closer to us, within the region where light can make progress toward us. The light has been travelling for billions of years, slowly making its way across expanding space, and it finally reaches us now, even though the galaxy that emitted it is now far beyond the horizon. The observable universe also tells us something profound about cosmic structure. Because we can only see a finite volume of space, we can only study the universe within that volume. Any claims we make about the universe as a whole are extrapolations based on what we observe within our horizon. For instance, we observe that the universe appears roughly the same in all directions. Galaxies are distributed fairly uniformly on large scales. The cosmic microwave background is nearly uniform, with only tiny temperature variations. This suggests the universe beyond our horizon is probably similar to what we see within it, but we cannot prove this. It is an assumption known as the cosmological principle, the idea that the universe is homogeneous and isotropic on large scales. That assumption might be wrong. Perhaps our observable universe is an unusual region, and the broader universe is different. Perhaps the laws of physics vary in distant regions we cannot see. We have no way to check. Our cosmic prison limits not just what we can observe, but what we can know. The Hubble Space Telescope and now the James Webb Space Telescope have pushed our view closer to the edge of the observable universe. JWST, with its incredible infrared sensitivity, can detect galaxies at redshifts of 13 or 14, meaning we are seeing them as they appeared just a few 100 million years after the Big Bang. We are looking at some of the first galaxies that ever formed, seeing the universe in its infancy. But even JWST cannot see beyond the particle horizon. No telescope ever will. The horizon is not a limitation of technology, it is a limitation of physics. Light from beyond that boundary has not had time to reach us, and if expansion continues accelerating, it never will. There is also a closer boundary worth mentioning, the surface of last scattering, the source of the cosmic microwave background radiation. This is the farthest back in time we can see using light. Before 380,000 years after the Big Bang, the universe was opaque, a hot, dense plasma where light could not travel freely. Any light emitted before that time was immediately absorbed and re-emitted, scattered endlessly through the plasma. When the universe cooled enough for atoms to form, light was finally able to travel freely. That moment, called recombination, is what we see when we observe the cosmic microwave background. It is the oldest light in the universe, a snapshot of the cosmos, when it was just 380,000 years old. We cannot see farther back than this using light. To probe earlier times, we would need different messengers, gravitational waves, neutrinos, or other particles that can pass through the opaque early universe. These might allow us to glimpse even closer to the Big Bang itself. But for now, the CMB represents our deepest view into cosmic history using electromagnetic radiation. So we find ourselves in a curious position. We live in a vast universe, but we can only observe a finite bubble. That bubble is large, 93 billion light-years across, but it is not everything. Beyond the horizon lies more universe, perhaps infinitely more, forever hidden from our view. It is a bit like being on an island in a fog-covered ocean. You can see the water around your island, out to where the fog blocks your view. You know there is more ocean beyond the fog. You can see waves coming from that direction, evidence that something is out there. But you cannot see the distant shores, cannot map the full extent of the sea. Your knowledge is limited to your visible horizon. And if the fog is getting thicker, as it is in our accelerating universe, your visible horizon is shrinking. You are seeing less and less of the ocean over time. This is our cosmic situation. We are islanders on a small planet, peering out through telescopes, mapping the visible universe, knowing that most of reality lies beyond our reach. It is humbling, it is isolating, and it is also strangely beautiful, this finite bubble of light and structure and history that we call home. We cannot see everything. We will never see everything, but we can see enough to understand the rules, to trace the history, to measure our little corner of infinity. And perhaps that is enough. Sit with that boundary. 46.5 billion light-years in every direction. Beyond that, mystery. Beyond that, forever unknown. We are prisoners of light and time, trapped inside an expanding sphere, watching the universe gradually fade from view. In 1964, two radio astronomers in New Jersey were trying to eliminate a persistent, annoying hiss from their antenna. Arno Penzias and Robert Wilson were working with a large horn-shaped radio telescope, preparing it for satellite communications research. But no matter what they did, they could not get rid of the background noise. They checked the electronics. They pointed the antenna in different directions. They even cleaned out pigeon droppings from inside the horn. Yes, pigeons had been nesting in their expensive scientific instrument, thinking perhaps that was causing the interference. The noise remained, a faint uniform microwave signal coming from every direction in the sky, day and night, summer and winter. It was always there, always the same strength, with a temperature of about 3 degrees above absolute zero. What Penzias and Wilson had accidentally discovered was the cosmic microwave background, the oldest light in the universe, the afterglow of the Big Bang itself. They had found the single most important piece of evidence for the Big Bang theory, and they had found it while trying to get rid of what they thought was an equipment malfunction. For this accidental discovery, they would win the Nobel Prize in Physics in 1978. The pigeons, sadly, received no recognition. But what exactly is the cosmic microwave background, and why is it so important? Let us go back to the beginning, not quite to the Big Bang itself, but close. In the first few 100,000 years after the Big Bang, the universe was hot and dense, filled with a plasma of protons, electrons, and photons. The temperature was thousands of degrees, hot enough to keep atoms from forming. The photons, particles of light, were constantly interacting with the charged particles, bouncing off electrons, getting absorbed and re-emitted. Light could not travel freely. The universe was opaque, like a thick fog where you cannot see more than a few feet in front of you. As the universe expanded, it cooled. Eventually, about 380,000 years after the Big Bang, it cooled enough for electrons to combine with protons and form neutral hydrogen atoms. This moment is called recombination, though that is a bit of a misnomer since the electrons and protons were combining for the first time, not recombining. When atoms formed, something remarkable happened. Photons suddenly had far fewer charged particles to interact with. Neutral atoms are much less effective at scattering light than free electrons. The fog lifted. The universe became transparent. It was like someone suddenly turning on the lights in a room, or, more accurately, like a fog suddenly clearing to reveal a vast landscape that was always there but could not be seen. The photons that were bouncing around in the plasma were suddenly free to travel through space, and they have been travelling ever since for 13.8 billion years, getting stretched and redshifted by the expansion of space, cooling from thousands of degrees to just under 3 degrees Kelvin. Those photons are what we detect as the cosmic microwave background. It is light from when the universe was 380,000 years old, preserved and cooled, reaching us from every direction. When you tune an old television to a channel with no signal and see static on the screen, about 1% of that static is actually the cosmic microwave background. You are seeing the afterglow of the Big Bang on your TV. The CMB is not coming from a specific place. It is coming from a specific time. Every point in space was filled with this hot plasma, and every point released its photons when recombination occurred. So no matter which direction we look, we see that moment, that surface of last scattering, surrounding us like a sphere. We are surrounded by it, bathed in it, immersed in a sea of ancient light. And here is the extraordinary thing. The cosmic microwave background is astonishingly uniform. No matter which direction you look in the sky, the CMB has almost exactly the same temperature, 2.725 Kelvin. Variations are tiny, just 1 part in 100,000. This uniformity tells us that the early universe was remarkably smooth and homogeneous. But those tiny variations, those 1 in 100,000 differences, are critically important. They represent slight density differences in the early universe, regions that were slightly hotter or cooler, slightly denser or less dense, and those tiny fluctuations were the seeds from which all cosmic structure grew. Regions that were slightly denser had slightly stronger gravity. They pulled in more matter. Over time, those overdense regions grew, attracting more and more material, eventually collapsing to form the first stars, then galaxies, then galaxy clusters. Everything we see in the universe today, every star, every galaxy, every structure grew from those tiny ripples in the cosmic microwave background. So when we map the CMB, we are not just seeing the universe as it was 13.8 billion years ago. We are seeing the blueprint for everything that came after. We are seeing the seeds of our own existence. Several missions have mapped the cosmic microwave background with increasing precision. COBE, the Cosmic Background Explorer, launched in 1989, made the first detailed measurements and confirmed that the CMB has a perfect blackbody spectrum, exactly what you would expect from the cooling radiation of the Big Bang. COBE also detected the tiny temperature variations, the anisotropies that would become so important. WMAP, the Wilkinson Microwave Anisotropy Probe, launched in 2001, produced much more detailed maps of the CMB, revealing the structure of those temperature fluctuations with unprecedented clarity. And Planck, a European Space Agency mission launched in 2009, provided the most precise measurements yet, mapping the CMB with extraordinary resolution and accuracy. These maps look almost like abstract art. Swirls of red and blue representing slightly warmer and cooler regions, patterns and structures that encode the physics of the early universe. But they are not art, they are data. And from that data we can extract an astonishing amount of information. The pattern of fluctuations in the CMB tells us about the composition of the universe. By analysing the sizes of the hot and cold spots, the statistical distribution of fluctuations, and the power spectrum, a mathematical description of how much variation exists at different scales, cosmologists can determine what the universe is made of. The answer turns out to be surprising. Ordinary matter, the stuff that makes up stars, planets and us, accounts for only about 5% of the universe's total energy content. Dark matter, which we cannot see but which exerts gravitational influence, makes up about 27%. And dark energy, the mysterious force driving the accelerated expansion of the universe, makes up about 68%. We are, quite literally, made of the minority component of the universe. Most of what exists is invisible to us. The CMB also tells us about the geometry of the universe. General relativity allows for 3 possible shapes. The universe could be positively curved, like the surface of a sphere, negatively curved like a saddle, or flat, like an infinite plane. The curvature affects how structures appear in the CMB, particularly the size of the largest hot and cold spots. Measurements from Dumap and Planck show that the universe is flat, or so close to flat that we cannot measure any curvature. Flat to within a margin of error of less than 0.5%. This flatness has profound implications. It suggests the universe is likely infinite in extent, stretching on forever in all directions. Our observable universe is just a finite bubble within an infinite cosmos. The CMB also provides a cosmic standard ruler, a known distance we can use to measure the universe. In the early universe, sound waves rippled through the plasma, creating pressure waves that propagated outward from density fluctuations. These waves travelled at a finite speed, and by the time recombination occurred, they had reached a specific distance from their starting points. That distance, about 450,000 light-years at the time, is imprinted in the pattern of the CMB. We call these imprints baryon acoustic oscillations, or BAO for short. They show up as a characteristic scale in the distribution of matter, both in the CMB and in the large-scale structure of galaxies today. Because we know the physical size of this scale, we can use it as a standard ruler to measure cosmic distances and the expansion rate of the universe. This is how the CMB contributes to measuring the Hubble constant, and interestingly, the value derived from CMB observations, about 67 kilometers per second per megaparsec, differs slightly from the value measured using the cosmic distance ladder, about 73. This discrepancy, the Hubble tension we mentioned earlier, remains unresolved. Either our measurements have subtle errors, or there is new physics we do not yet understand. One particularly fascinating aspect of the CMB is what it tells us about the universe's age and expansion history. By fitting models to the CMB data, cosmologists can determine not just what the universe is made of now, but how its composition has changed over time, how fast it was expanding at different epochs, and how old it is. The current best estimate from Planck data is that the universe is 13.797 billion years old, give or take a few tens of millions of years. That might seem like a large uncertainty, tens of millions of years, but consider that we are measuring the age of the entire universe. Being accurate to within a fraction of a percent is rather impressive. The CMB also potentially contains evidence of inflation, a brief period of exponential expansion, in the first fraction of a second after the Big Bang. Inflation theory predicts that quantum fluctuations during this period would have been stretched to cosmic scales, creating the initial density variations we see in the CMB. The patterns in the CMB are consistent with these predictions, providing strong support for inflation. Some inflationary models also predict that gravitational waves generated during inflation should leave a specific signature in the polarization of the CMB, a pattern called B-mode polarization. Several experiments are currently searching for this signature. If found, it would provide direct evidence of inflation and give us a window into physics at energy scales far beyond anything we can achieve in particle accelerators. There is something deeply humbling about the fact that our best picture of the early universe comes from a signal that two radio astronomers initially thought was equipment noise. The cosmic microwave background was not predicted and then discovered through careful observation. It was discovered by accident and only afterward recognized for what it was. The theoretical prediction had been made years earlier by physicists George Gamow, Ralph Alpher, and Robert Herman, but their work had been largely forgotten by the time Penzias and Wilson stumbled onto the signal. Science sometimes works that way. The universe reveals its secrets in unexpected moments, to people who are paying attention even when they are looking for something else. The greatest discoveries sometimes come not from grand expeditions, but from noticing the thing that does not quite fit, the noise that should not be there. When you look at maps of the cosmic microwave background, you are looking at the universe when it was young, a baby, cosmically speaking, just learning to become transparent. You are seeing the structure from which everything we know emerged. Every galaxy, every star, every planet, every person. All of it grew from those tiny ripples of slightly denser and less dense regions imprinted in that ancient light. The CMB is a gift. It is a direct view of the early universe, a fossil record of conditions just after the Big Bang, a way to test our cosmological theories against hard data. Without the CMB, we would know far less about the universe's composition, age, geometry, and history. It is one of the pillars of modern cosmology, right alongside Hubble's observations of expansion and the large-scale structure of galaxies. And it all started with two scientists trying to eliminate annoying noise from their antenna. They thought they were cleaning up interference. They were actually listening to the echo of creation itself. Sometimes the most profound discoveries come from the most mundane investigations. Sometimes the signal you are trying to remove is actually the most important signal of all. Let that ancient light wash over you. 380,000 years after the Big Bang, photons became free. 13.8 billion years later, they reach us, carrying stories from the universe's infancy. We are reading the universe's baby picture, and it tells us how we came to be. On Christmas Day 2021, a telescope the size of a tennis court, folded up like the world's most expensive piece of origami, launched into space atop a rocket from French Guiana. It would take a month to reach its destination, a gravitationally stable point a million miles from Earth called L2. It would take another 5 months to unfold, align its mirrors and calibrate its instruments. And when it finally opened its eyes and looked out at the universe, it would see farther and more clearly than any telescope before it. The James Webb Space Telescope, named after NASA's second administrator, represents a leap in observational capability comparable to Galileo's first telescope or the launch of Hubble. It is not just incrementally better than previous telescopes, it is transformatively better. JWST was designed to see the first galaxies that formed after the Big Bang, to peer through cosmic dust to watch stars being born, to analyze the atmospheres of planets around other stars. It was built to answer some of the biggest questions in astronomy. When did the first stars ignite? How do galaxies evolve? What are exoplanet atmospheres made of? And perhaps most relevant to our story, how far can we actually see? The answer to that last question turned out to be farther than we expected. JWST is primarily an infrared telescope. Unlike Hubble, which observes mostly visible light, JWST sees the universe in wavelengths, just beyond what our eyes can detect. This might seem like a limitation, but it is actually a superpower for studying the early universe. Remember redshift. As light travels through expanding space, its wavelength gets stretched. Light that was originally emitted as visible light billions of years ago has been stretched into the infrared by the time it reaches us. The most distant galaxies, the ones we most want to see, have been redshifted so much that they are essentially invisible to telescopes like Hubble. But they are perfectly visible to JWST. Infrared vision also allows JWST to see through cosmic dust. Dust clouds that block visible light are transparent to infrared, like fog disappearing when you switch to infrared goggles. This lets JWST peer into stellar nurseries, watching stars form inside clouds of gas and dust, seeing processes that were previously hidden from view. The telescope itself is an engineering marvel. Its primary mirror is composed of 18 hexagonal segments made of gold-plated beryllium, arranged in a honeycomb pattern. Gold is an excellent reflector of infrared light, and beryllium is both strong and lightweight, crucial when you need to launch your telescope into space. The mirror segments can be individually adjusted with nanometer precision, allowing the telescope to maintain perfect focus despite the temperature swings of space. Behind the mirror sits a sun shield the size of a tennis court, made of 5 layers of material thinner than a human hair. This sun shield protects the telescope from the sun's heat, keeping the instruments cold enough to detect faint infrared signals from the distant universe. JWST operates at around -230 degrees Celsius, colder than the surface of Pluto. Everything about JWST had to be folded for launch and then unfold in space. The mirror segments, the sun shield, the secondary mirror support structure. It was the most complex origami project ever attempted, with hundreds of potential failure points. Engineers called the deployment sequence 30 days of terror, because if anything went wrong, there would be no way to fix it. JWST orbits too far from Earth for a repair mission. But everything worked. Every motor, every cable, every latch performed exactly as designed. The telescope unfolded, aligned, and began sending back images that left astronomers speechless. The first deep field image, released in July 2022, showed thousands of galaxies in a patch of sky smaller than a grain of sand held at arm's length. Galaxies stretched and distorted by gravitational lensing. Galaxies so distant their light had been travelling toward us for over 13 billion years. And all of this in an exposure that took just 12.5 hours, something that would have taken Hubble weeks to accomplish. But the real revelations came when astronomers started measuring distances. JWST has discovered galaxies at redshifts of 13, 14, and possibly higher. These are galaxies forming just 200 to 300 million years after the Big Bang. We are seeing the universe at about 2% of its current age, watching the first generation of galaxies assemble from the primordial gas clouds. And here is where things got interesting. Some of these early galaxies are surprisingly massive and mature. According to our models of galaxy formation, the first galaxies should be small, messy, irregular, just beginning to pull themselves together from the primordial gas. But JWST is finding galaxies at Z equals 13, that already contain billions of stars, that already show signs of structure and organization, that already look more like mature galaxies than cosmic toddlers just learning to walk. This has created what some astronomers are calling the impossibly early galaxy problem. How did these galaxies get so big, so fast? Did star formation happen more efficiently in the early universe than we thought? Did the first stars form earlier than our models predict? Or are we fundamentally misunderstanding something about how galaxies assemble? The answer is still being debated. Some of the initial distance measurements may have been overestimated. Determining precise redshifts is tricky, and photometric redshifts, which estimate distance based on color, can sometimes be fooled. But even accounting for potential errors, it is clear that galaxies formed faster and more efficiently in the early universe than we expected. JWST is also revealing galaxies in a period called the Epoch of Reionization, when the first stars and galaxies began producing enough ultraviolet light to ionize the hydrogen gas that filled the universe. Before this epoch, the universe had cooled after recombination and entered a dark age. No stars yet, just neutral hydrogen fog settling over everything like cosmic twilight. The first stars ended this dark age, their light gradually clearing the fog, making the universe transparent again. JWST can see this process happening. It can identify galaxies that are actively ionizing their surroundings, watch the bubbles of ionized gas expand and merge, and trace how the universe transitioned from opaque to transparent. This is history written in light, the story of how the universe became the place we see today. One of the most remarkable discoveries involves gravitational lensing. When light from a distant galaxy passes near a massive galaxy cluster, the cluster's gravity bends the light, magnifying and distorting the background galaxy. This natural telescope effect can make extremely distant galaxies visible that would otherwise be too faint to detect. JWST has used gravitational lensing to see galaxies at record distances, galaxies that existed just a few 100 million years after the Big Bang. These galaxies appear as stretched arcs or multiple images around the lensing cluster, distorted but magnified, allowing us to study their properties in detail. One such galaxy, recently confirmed at a redshift of around 14, is currently among the most distant objects ever observed. When we see this galaxy, we are looking back to a time when the universe was only about 300 million years old, just 2% of its current age. This galaxy's light has been traveling toward us for over 13.5 billion years. But there is something important to remember, that galaxy is not 13.5 billion light years away. The light has been traveling for 13.5 billion years, but during that time, space has been expanding. The galaxy is now much farther away, perhaps 33 or 34 billion light-years distant, measured in today's coordinates. This is the strange arithmetic of cosmology. Distance and time are not the same thing in an expanding universe. JWST is not just looking at galaxies, it has also been studying closer objects in extraordinary detail. It has analysed the atmospheres of exoplanets, planets orbiting other stars, detecting water vapour, carbon dioxide, sulfur dioxide, and other molecules in their atmospheres. It has imaged Neptune's rings with stunning clarity, revealing structures that had not been seen since Voyager flew past in 1989. It has watched stars explode and traced the expanding debris as supernova remnants. It has observed the supermassive black hole at the centre of our galaxy, watching material orbit and occasionally fall in. But for our story, the story of measuring the universe, JWST's most important contribution is pushing the observable universe's edge closer to our view. Every distant galaxy it detects, Every redshift it measures, every early structure it reveals, helps us understand how the universe evolved from the smooth plasma of the cosmic microwave background to the rich tapestry of galaxies we see today. JWST is also contributing to the Hubble tension. By observing Cepheid variables in distant galaxies with greater precision than ever before, JWST is helping refine the cosmic distance ladder. Early results suggest the Hubble Space Telescope's measurements were correct. The expansion rate does seem to be around 73 kilometers per second per megaparsec, at least when measured using the distance ladder. This deepens the mystery of why that value does not match the 67 from the cosmic microwave background. Perhaps the most profound thing JWST has shown us is simply how much we still have to learn. Every image reveals new puzzles. Every spectrum raises new questions. The early galaxies are more massive than expected. Star formation happened earlier than predicted. The first black holes grew faster than our models allow. These are not failures of science. They are invitations to dig deeper, to refine our theories, to understand the universe more completely. Every time we build a better telescope, we discover that reality is more complex and more interesting than we imagined. This is how science works, not by confirming what we already believe, but by showing us where our understanding is incomplete. There is a photograph that many people saw when JWST's first images were released, the deep field image showing thousands of galaxies. In that image, nearly every point of light is a galaxy containing hundreds of billions of stars. Some of those galaxies are gravitationally lensed, appearing multiple times in stretched arcs. Some are spiral galaxies like our own Milky Way. Some are elliptical galaxies, ancient and red. Some are irregular, chaotic, still forming. And this is just one tiny patch of sky, one random direction among thousands of possible directions. The same view exists everywhere. Every direction you look, thousands of galaxies, billions upon billions of them, filling the observable universe. JWST lets us see them. It lets us measure them. It lets us trace their evolution across cosmic time, watching how they grow and change and merge, how they form stars and planets, how they create the conditions for complexity and perhaps for life. It is a time machine showing us the universe's history written in light. It is a measuring tool extending our cosmic yardsticks to the edge of the observable universe. And it is a reminder of how much we can achieve when we build our instruments carefully, launch them successfully, and point them at the sky with curiosity and wonder. The mission was decades in the making. Planning began in the 1990s. Construction took years. Delays pushed the launch back repeatedly. The budget ballooned from $500 million to $10 billion. Many wondered if it would ever launch, if it would ever work. But it did. And now, floating silently at L2, JWST is rewriting astronomy textbooks, one observation at a time. The universe is vast. JWST is just one telescope, one set of eyes, one small instrument floating 1 million miles from Earth. But what eyes they are, what a view they provide. Imagine floating beside JWST at L2, looking out at the universe through gold-plated mirrors, seeing light that has travelled for 13 billion years, watching galaxies form in the cosmic dawn. The universe is showing us its history, and we are finally learning to read it. In 1998, 2 teams of astronomers were racing to answer what seemed like a straightforward question. How fast is the universe's expansion slowing down? Everyone knew the universe was expanding. Hubble had proven that 70 years earlier, and everyone assumed that expansion must be decelerating. After all, gravity pulls everything together. The mutual gravitational attraction of all the matter in the universe should be gradually slowing the expansion, like a ball thrown upward that slows as Earth's gravity pulls it back down. The question was just how much the expansion was slowing. Was it slowing enough that the universe would eventually stop expanding and collapse back on itself in a big crunch? Or was the initial expansion velocity high enough that the universe would expand forever, just at an ever-decreasing rate? Both teams, the Supernova Cosmology project led by Saul Perlmutter and the HISE Supernova Search team led by Brian Schmidt and Adam Rees, use Type Ia supernovae to measure distances to very remote galaxies. These exploding stars, as we discussed earlier, make excellent standard candles because they have consistent brightness. Measure how bright they appear and you can calculate how far away they are. The teams found distant supernovae, measured their redshifts to determine how fast their host galaxies were receding, calculated distances from their brightness, and plotted the results. Distance versus redshift. The shape of that relationship would reveal how much the expansion had been slowing over cosmic time. But when they analysed their data, something was wrong. The distant supernovae were dimmer than expected. Dimmer meant farther away. Farther away meant the universe had expanded more than predicted. The expansion was not slowing down, it was speeding up. At first, both teams thought they had made a mistake. They checked their measurements. They looked for sources of error. They wondered if distant supernovae might be intrinsically dimmer than nearby ones, or if dust was absorbing some of the light. They scrutinized their assumptions, their calibrations, their data analysis pipelines. But the more they checked, the more certain they became. The data was solid. The universe really was accelerating. This was not supposed to be possible. Imagine throwing a ball upward and watching it slow down as expected, then watching it suddenly start accelerating upward, as if gravity had reversed. That is essentially what the universe is doing. Not only is space expanding, carrying galaxies apart, but that expansion is getting faster over time. Something is pushing space apart, something with enough influence to overcome the gravitational attraction of all the matter in the universe, something we had never detected or predicted. They called it dark energy. The name is a placeholder, really. We call it dark because we cannot see it, and energy because it seems to act like a form of energy inherent to space itself. But we do not actually know what it is. It is one of the deepest mysteries in physics, possibly the deepest mystery, given that it makes up more than 2/3 of everything that exists. Dark energy makes up about 68% of the universe's total energy content. Dark matter, the invisible stuff that holds galaxies together, makes up about 27%. Ordinary matter, the atoms that make up stars and planets and us, accounts for just 5%. We live in a universe where 95% of the content is invisible to us. We are the minority component, the small fraction of normal matter floating in a cosmos dominated by things we do not understand. The discovery of accelerating expansion earned Perlmutter, Schmidt, and Rees the Nobel Prize in Physics in 2011. It also fundamentally changed our understanding of the universe's past and future. If dark energy continues to dominate, and all evidence suggests it will, the universe will expand forever, accelerating without limit. Distant galaxies will recede faster and faster. The space between galaxy clusters will grow at an ever-increasing rate. And eventually, billions of years from now, almost everything beyond our local gravitational neighborhood will disappear beyond the cosmic horizon. Let us think about what this means for the observable universe. Right now we can see galaxies that are receding from us faster than the speed of light. This sounds impossible, but as we discussed, it is not. They are not moving through space faster than light. Space itself is expanding and carrying them along. We can see these galaxies because their light left them billions of years ago when they were closer and the light could make progress toward us. But there is a boundary, the cosmological event horizon, beyond which galaxies are receding so fast that light emitted from them now will never reach us. Ever. Even if we wait trillions of years, that light will never arrive, because the space between us and them is expanding faster than light can cross it. Dark energy is pushing this horizon closer to us over time. In the far future, trillions of years from now, observers in our galaxy will only be able to see the galaxies in our local group. The Milky Way, Andromeda, and a few dozen smaller galaxies that are gravitationally bound together. Everything else will have been carried beyond the horizon by accelerating expansion. The night sky will be much emptier, much lonelier. Future astronomers, if they exist, will look out at the universe and see almost nothing. No distant galaxies, no cosmic microwave background. It will have redshifted into undetectability. No evidence that the universe is expanding because everything observable will be gravitationally bound and not participating in the expansion. They will be cosmologically isolated. They will have no way to know that billions of other galaxies once filled the observable universe, that the cosmos is vast and ancient and expanding. The evidence will have disappeared beyond the reach of light. This means we are living in a privileged time. Right now, we can observe the full history of the universe. We can see the cosmic microwave background from 380,000 years after the Big Bang. We can see distant galaxies forming in the first few 100 million years. We can trace the evolution of structure across 13.8 billion years. We can measure the expansion rate and deduce the presence of dark energy. Future civilizations will not have that privilege. The universe will have pulled its curtains closed, hiding most of its history beyond the horizon. There's something melancholy about this. The universe is not just vast, it is getting vaster. The boundary of what we can observe is not fixed, it is shrinking, at least in terms of what new information can reach us. We are watching the universe gradually isolate itself, piece by piece, galaxy by galaxy, slipping beyond the edge of detectability. But what exactly is dark energy? The simplest explanation is that it is the cosmological constant, a term Einstein added to his equations of general relativity to keep the universe static. He thought the universe was eternal and unchanging, so he introduced a repulsive force to balance gravity and prevent collapse. When Hubble discovered expansion, Einstein removed the cosmological constant, reportedly calling it his biggest blunder. But it turns out Einstein might have been right after all, just not in the way he intended. The cosmological constant represents energy inherent to empty space itself. Even vacuum, even nothing, has energy. Quantum mechanics tells us that empty space is not truly empty. It seethes with virtual particles popping in and out of existence with quantum fluctuations at the smallest scales. This quantum activity contributes energy to the vacuum. And that vacuum energy has a strange property. As space expands, creating more volume, the total amount of vacuum energy increases. Unlike matter, which gets diluted as space expands, vacuum energy density remains constant. More space means more vacuum energy. This creates a repulsive effect. The more space there is, the stronger the push. As the universe expands, dark energy becomes increasingly dominant, accelerating the expansion faster and faster. If dark energy is indeed the cosmological constant, if it is truly the energy of empty space, then its density should remain constant forever. The acceleration should continue indefinitely. The universe will expand exponentially faster and faster, eventually reaching a state where almost everything is beyond our horizon. But there are other possibilities. Perhaps dark energy is not constant. Perhaps it is a field that varies over time, something called quintessence. Perhaps it will strengthen, leading to a big rip, where the expansion becomes so violent that it tears apart galaxies, then stars, then planets, then eventually atoms themselves. Or perhaps it will weaken, allowing gravity to regain dominance, possibly even leading to a big crunch after all. We do not know. We cannot yet measure whether dark energy is changing over time. Its effects are subtle, detectable only across vast distances and cosmic timescales. We are still gathering data, still refining our measurements, still trying to understand what this mysterious force actually is. What we do know is that dark energy is real. The supernovae data has been confirmed by multiple independent observations. The cosmic microwave background shows it. Large-scale structure surveys show it. Gravitational lensing shows it. Every measurement agrees. The universe is accelerating. This changes everything about how we measure cosmic distances and understand the universe's geometry. When we say the observable universe is 93 billion light-years across, we are accounting for accelerating expansion. When we calculate how far away distant galaxies are, we have to factor in how dark energy has affected space over the billions of years the light was traveling. Dark energy also affects the ultimate fate of the universe. In a decelerating universe, distances would eventually stabilize or even reverse. In an accelerating universe, distances will grow without limit. The cosmic horizon will close in around us. Most of the universe will become forever unreachable, forever unknowable. There is something profound about this. We live at a moment in cosmic history when the universe is still revealing itself, when we can still see evidence of the Big Bang, when we can still trace the evolution of galaxies across most of cosmic time, when we can still detect the cosmic microwave background and measure the expansion rate. In a few trillion years, none of this will be possible. The universe will have aged, and in aging, will have hidden most of its history from view. The cosmic fossil record will have eroded beyond recovery. We are cosmological archaeologists working in a narrow window of time, reading the fossil record before it vanishes beyond the horizon. We are observers who can still see the full story, still piece together the narrative from beginning to nearly present. The universe is giving us a gift, the ability to understand it, but that gift is temporary. Dark energy has set an expiration date on cosmic knowledge. Dark energy ensures that the edge we are measuring, the boundary of the observable universe, is not just distant but receding. We're not just measuring space. We are measuring something that is actively moving away from us, pulling more and more of the cosmos beyond our reach. It is a strange kind of measurement. We are quantifying not just what exists, but what will eventually be lost. We are marking the boundary of the knowable before it slips into the unknowable. We are witnesses to a universe that is slowly, peacefully, inexorably saying farewell to most of itself. And yet, there is beauty in this too. The fact that we exist now, in this particular epoch, when the universe is still observable, when we can see its history, measure its expansion, deduce its composition, is itself remarkable. We are living in what might be the only era where the full cosmic story can be read. Sit with that strangeness. The universe is not just expanding, it is accelerating, pulling away from us, gradually disappearing beyond the speed of light. We are living in the golden age of cosmology. We can see almost everything, but the clock is ticking and the universe is slowly, inexorably saying goodbye. Here is a strange fact about the human brain. It cannot actually comprehend large numbers. Try to visualize 1 million. Not the word million, Not the concept, but the actual quantity. 1,000,000 individual objects. You cannot do it. Your brain will give you a vague sense of very many, but it will not show you 1,000,000 distinct things. The number is simply too large. Now try to visualize 93 billion light years. Each light year is 6 trillion miles, 93 billion of them, the diameter of the observable universe. Your brain offers you nothing, perhaps a feeling of vastness, perhaps a slight sense of vertigo, but no actual comprehension. We are creatures who evolved on the African savanna, where the farthest we could see was a few miles to the horizon. Our brains are optimized for human-scale distances and human-scale numbers. We understand 3 gazelles and 5 days' walk. We do not understand 2 trillion galaxies or 13.8 billion years. And yet, here we are, trying to measure and comprehend the entire universe. This creates a peculiar tension. We have the mathematics to calculate cosmic distances. We have the instruments to observe the edge of the observable universe. We can write down the numbers, manipulate them, use them to make predictions, but we cannot feel them. We cannot hold them in our minds the way we can hold the concept of 10 or 100. The universe is incomprehensibly large, and we are incomprehensibly small within it. This realization affects people differently. For some, it triggers existential dread. What does human life mean in a cosmos 93 billion light-years across? What significance can our brief existence possibly have when we live on a speck of dust, orbiting an ordinary star in an ordinary galaxy that is one of 2 trillion galaxies? For others, it brings a strange kind of peace. If we are that small, then our problems are small too. Our anxieties, our failures, our embarrassments, all of it shrinks to nothing against the cosmic scale. There is freedom in insignificance. And for some, it simply inspires wonder. The fact that we, collections of atoms that briefly think and feel, can look out at the universe and understand it, measure it, trace its history across billions of years, that itself seems miraculous. The ancient Greeks had a word for the ordered universe, cosmos. It meant not just the physical universe, but the idea that the universe was comprehensible, that it followed rules, that it could be understood. The opposite of cosmos was chaos, disorder, meaninglessness, incomprehensibility. When we measure the universe, we are transforming chaos into cosmos. We are taking the overwhelming vastness of reality and making it legible, translating it into numbers and equations and maps that our small human minds can work with. But the cosmos keeps insisting on its incomprehensibility. Every time we think we have grasped its scale, it reveals itself to be larger. Every time we think we understand its composition, we discover we were only seeing 5% of what exists. The observable universe is 93 billion light-years across, but the actual universe, the whole thing beyond our horizon, might be infinite. Infinity is not just a very large number. It is a fundamentally different category of thing. You cannot add to infinity. You cannot multiply it. It simply is, eternally and completely beyond measure. If the universe is infinite, then it contains infinite matter, infinite energy, infinite galaxies. Somewhere in that infinity, every possible configuration of atoms exists, including exact copies of you, living slightly different lives, including copies of Earth where history went differently, including configurations so bizarre and unlikely that they seem impossible. But in an infinite universe, even the impossible happens somewhere, infinitely many times. This is deeply unsettling to contemplate, not just because infinity is incomprehensible, but because it removes specialness. If everything happens somewhere in an infinite universe, then nothing is unique. Your exact life, Your exact thoughts, your exact experiences, they are all being lived by infinite copies of you scattered across infinite space. But we do not know if the universe is infinite. We only know that it is at least much larger than what we can see. Perhaps it is finite but unbounded, shaped like the three-dimensional surface of a four-dimensional sphere. Perhaps it has an edge somewhere, far beyond our reach. We cannot know. We can only measure our bubble, our observable patch, the finite sphere from which light has had time to reach us. And that not knowing is itself a kind of answer. There are limits to what we can measure. There are questions we can ask, but not answer. The universe does not owe us comprehensibility. Psychologically, humans do not handle scale well. Studies have shown that when numbers get large enough, they lose meaning. 1,000 deaths in a disaster feels tragic. 10,000 deaths feel about the same. Our emotional response does not scale linearly with numbers. We have compassion fatigue built into our neurology. And the same thing happens with cosmic scales. 10 billion light-years and 90 billion light-years feel approximately the same. Both are just incomprehensibly far. We lose the ability to distinguish between scales of vastness. But we can use analogies. We can scale the universe down to sizes we understand. If the sun were the size of a grapefruit, Earth would be a grain of sand about 25 yards away. The nearest star would be another grapefruit 2,000 miles away. The Milky Way galaxy would be about 20 million miles across. And the observable universe would be, well, still incomprehensibly large, even at this scale. Or try this. If you could somehow compress the entire observable universe so that the distance to the nearest star, 4.2 light-years, was reduced to 1 inch, then the observable universe would be about 440 million miles across, still larger than the orbit of Mars. These analogies help, but they also reveal the problem. Even when we shrink the universe down, it remains too large to grasp. The scale defeats us. And yet, we keep measuring. We keep building telescopes, analyzing spectra, calculating distances. We keep pushing against the boundaries of what we can know, even though we know those boundaries are fundamentally limited by light speed and expansion and the finite age of the universe. Why do we do this? What psychological drive compels us to measure the unmeasurable? Perhaps it is the same drive that made Eratosthenes measure the Earth using shadows and wells, the same curiosity that made Bessel spend a year watching a dim star shift against the background, the same wonder that makes us point telescopes at tiny patches of empty sky and discover thousands of galaxies. We measure because we can, because our minds, limited as they are, can nevertheless grasp patterns. We can understand rules. We can build ladders of inference that reach across billions of light-years. We cannot visualize 93 billion light-years, but we can calculate it. We can trace the logic of redshift and expansion and cosmic history and arrive at that number with confidence. We can hold the concept, even if we cannot hold the scale. There is something profoundly human about this. We are not content to simply exist. We want to understand where we are. We want to know the size of the stage on which we stand, even when that stage is so vast that our minds cannot contain it. The astronomer Carl Sagan famously said, "The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself." This is not just poetic language. It is literally true. The atoms in your body were forged in stars that exploded billions of years ago. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was created in the nuclear furnaces of stars, or in the violent explosions that ended their lives. You are a temporary arrangement of stardust, that has become conscious, aware, capable of looking out at the universe and understanding it. You are also incomprehensibly small. If the universe is 93 billion light-years across and you are about 6 feet tall, then you are 1 part in 5.5 times 10 to the 28th of the observable universe. That is a 28-digit denominator. You are vanishingly tiny. And yet you exist. You think. You wonder. You can understand that you are tiny. You can measure the thing that dwarfs you. There is a philosophical movement called Cosmicism, associated with the writer H.P. Lovecraft, that emphasizes humanity's cosmic insignificance as a source of existential horror. The universe is vast and indifferent. We are nothing. Our existence means nothing. The appropriate response is terror and despair. But there is another way to view it. Yes, we are small. Yes, the universe is vast. Yes, most of reality is beyond our reach, hidden behind cosmic horizons, made of dark matter and dark energy we cannot see or understand. But we are here, against absurd odds in a universe that is mostly empty space and dark energy, on a planet at just the right distance from just the right kind of star. Atoms have arranged themselves into patterns complex enough to think, to feel, to measure the cosmos. We are improbable. We are temporary. We are fragile, but we are also remarkable. The universe is 93 billion light-years across. We have measured it. With shadows and parallax and pulsing stars and exploding stars and the afterglow of creation itself, we have built a ladder that reaches from Earth to the edge of observable reality. We cannot comprehend the scale, but we can acknowledge it. We can sit with it. We can let it wash over us. The vastness, the age, the incomprehensible distances. And we can recognize that there is something beautiful about being small. It means we are part of something larger. It means we belong to the cosmos, even if we are just tiny, brief sparks within it. The ancient Greek philosopher Democritus said, "In reality, there are only atoms and the void." He was wrong about the details. Atoms are not the fundamental particles, but he was right about the spirit of the claim. We are temporary arrangements of matter, briefly conscious, briefly able to observe and think and wonder. And then we return to the cosmos that made us. This is not depressing. This is just reality. And reality, as vast and strange as it is also the only place where beauty and love and understanding can exist. The universe may be indifferent to our existence, but we are not indifferent to it. We care, we wonder, we measure. And that caring, that wondering, that measuring, those are real things happening in a real universe. We live with infinity by accepting that we cannot comprehend it. We live with cosmic scale by acknowledging our smallness. We live with the knowledge that most of the universe is forever beyond our reach by appreciating what we can reach. We live by measuring what we can, wondering about what we cannot, and finding meaning not in cosmic significance, but in the brief, improbable fact of our existence. The astronaut Edgar Mitchell, who walked on the moon during Apollo 14, experienced what he called a profound shift in consciousness on the journey back to Earth. Looking out at the planet from space, seeing it suspended in the void, he felt a deep connection to all of existence. He called it the overview effect, a cognitive shift that comes from seeing Earth from space, recognizing our fragility and our interconnection. Many astronauts report similar experiences. From space, national borders disappear. Political conflicts seem trivial. The thin blue line of our atmosphere looks impossibly fragile, and the overwhelming sense is one of unity. We are all on this small planet together, floating in the vastness. You do not need to go to space to experience something similar. You just need to spend time contemplating cosmic scale, to really sit with the numbers, the distances, the age, to let yourself feel how small you are, how brief your existence is, how vast the universe is beyond you. And then notice what happens. For many people, that contemplation does not produce despair. It produces gratitude, gratitude for existence itself, gratitude for consciousness, gratitude for the improbable fact that the universe made a way to look at itself and understand itself. 93 billion light years, we measured it. Against all odds, with shadows and geometry and pulsing stars and ancient light, we figured out the size of everything we can possibly see. Thank you for joining me on this journey to the edge of the observable universe. If you would like to keep exploring the cosmos with me, subscribe to the Sleepy Astronomer for more peaceful journeys through space and time. There is always more to discover, more mysteries to contemplate, more wonder to experience. The stars will still be there tomorrow night, steady and eternal, beautiful and mysterious. They will be waiting for you, as they always have been, as they always will be. Sweet dreams under the stars. This is the Sleepy Astronomer, wishing you restful sleep and cosmic dreams. Good night.